The development of space-time view of quantum electrodynamics. We have a habit in writing articles published in scientific journals to make the work as finished as possible, to cover all the tracks, to not worry about the blind alleys, or to describe how you had the wrong idea first, and so on. So there isn't any place to publish in a dignified manner what you actually did in order to get to do the work. Although there has been in these days some interest in this kind of thing. Since winning the prize is a personal thing, I thought it could be excused in this particular situation if I were to talk personally about my relationship to quantum electrodynamics, rather than to discuss the subject itself in a refined and finished fashion. Furthermore, since there are 3 people who have won the prize in physics, if they're all going to be talking about quantum electrodynamics itself, one might become bored with the subject. So what I would like to tell you about today are the sequence of events, really the sequence of ideas which occurred, and by which I finally came out the other end with an unsolved problem for which I ultimately received a prize. I realized that a truly scientific paper would be of greater value, but such a paper I could publish in regular journals. So I shall use this Nobel lecture as an opportunity to do something of less value, but which I cannot do elsewhere. I ask your indulgence in another manner. I shall include details of anecdotes, which are of no value either scientifically nor for understanding the development of ideas. They are included only to make the lecture more entertaining. I worked on this problem about 8 years until the final publication in 1947. The beginning of the thing was at the Massachusetts Institute of Technology when I was an undergraduate student reading about the known physics, learning slowly about all these things that people were worrying about, and realizing ultimately that the fundamental problem of the day was that the quantum theory of electricity and magnetism was not completely satisfactory. This I gathered from books like those of Hitler and Dirac. I was inspired by the remarks in these books, not by the parts in which everything was proved and demonstrated carefully and calculated, because I couldn't understand those very well. At the young age, what I could understand were the remarks about the fact that this doesn't make any sense. In the last sentence of the book of Dirac, I can still remember. It seems that some essentially new physical ideas are here needed. So I had this as a challenge and an inspiration. I also had a personal feeling that since they didn't get a satisfactory answer to the problem I wanted to solve, I don't have to pay a lot of attention to what they did do. I did gather from my readings, however, that 2 things were the source of the difficulties with the quantum electrodynamic theories. The first was the infinite energy of interaction of the electron with itself, and this difficulty existed even in the classical theory. The other difficulty came from some infinities, which had to do with the infinite number of degrees of freedom in the field. As I understood at the time, as nearly as I can remember, this was simply the difficulty that if you quantize the harmonic oscillators of the field, say in a box, each oscillator has a ground state energy of 1/2 h bar omega. And there is an infinite number of modes in a box of every increasing frequency omega, and therefore there's an infinite energy in the box. I now realize that that wasn't a completely correct statement of the central problem. It can be removed simply by changing the zero from which energy is measured. At any rate, I believe that the difficulty arose somehow from a combination of the electron acting on itself and the infinite number of degrees of freedom of the field. All right, I could continue and read this entire Nobel lecture, but that would be definitely a different episode than what we're doing. So first of all, what are you watching?
That's what I want to know.
That's what everyone wants to know. All right, this is SG2 on space, or rather maybe we changed it to a different name that I can hardly remember. It's been a few months, as a disembodied voice in the background will say. Let me bring him on. I'm Shen, by the way. Let me see. Who is this guy? Who is this person right here? You're muted. If you're trying to talk, doesn't work well.
Muted. I'm not muted.
Now you're not muted.
Who is this guy?
Yeah. Who? Okay. This is. Okay. It's Leonard Kramer with your signature headband and new art pieces behind you. I see. I like that one that's right above your head.
Oh, that one.
Yeah, that one. Yeah, that's a new one. I think.
That's a new one. Yeah, that was inspired by a trip I took out to Big Bend Country in West Texas. I guess in April or March of last year, almost a year ago.
Wow, wonderful. I feel like I gotta take a trip like that sometime.
So,
Not sure when.
So what are we doing? I mean,
yeah. So
you know,
with that said, I was quoting for our viewers out there. You can probably tell I was reading from in Leonard as well, like the Nobel Prize in Physics, 1965, by the famed physicist Richard Feynman. Like, I have a bunch of his books. This is a picture of him. I actually have like 5 other books by him, but nothing apparently related to quantum electrodynamics, which is the topic we're trying to address today.
Well, he wrote a book. He wrote a book called he wrote a book.
Mm-hmm.
And it was called QED.
QED, that's the name?
That's the name of the book, QED.
So anybody could actually go and just read it, right?
And I've read the book. I haven't written it. I didn't reread it recently, but it's sort of delightful. I mean, it's not. I've exposed a few people to. That's kind of a funny way of saying that. I've introduced it to some people and have urged them to try to read it. Some people don't have too much difficulty with it, but it's written in a way that is meant to be a popular exposition of this theory that I guess he basically won the Nobel Prize for, right? And so it has a number of chapters in it, and this actually the book actually has the famous quote. Richard Feynman is often quoted as saying, you know, don't worry about if you don't understand quantum mechanics. My students don't understand quantum mechanics. I don't understand quantum mechanics, right? And this is the origin of that quote, and it's right there in the first few paragraphs.
It's in this book. Let me see if I can find it. But in the meantime, I mean, from what I guess this was back in the early, I mean, I don't know, 1930s or something, that or 40s.
It was after the Second World War.
After the Second World War, right?
Probably around 19. Actually, let me.
You're rustling through papers as well.
I have my.
Oh my gosh, you have his book. Well, of course you do. Like you just said it.
Yeah. He said, it's my task to convince you not to turn away because you don't understand it. That is because I don't understand it.
Okay.
Nobody does. And then he goes on to start talking about this in a way that he largely avoids mathematics. And he has and in his style, inimicable style, he has a very original approach to how to explain the interference of the photons or quantum mechanics. And actually. You mentioned some anecdotes, you know. So there's, you know, I've read about Richard Feynman for, you know, many years, and one of the anecdotes has to do with in the late 40s, physicists were trying to calculate a property of the electron, which is called its magnetic moment. It's sort of a single parameter that characterizes the magnetic field from electric current. All right, but the particular an electron has this property, and so the electron acts like a tiny little bar magnet. And if you put the magnetic field, if you put the electron in a magnetic field, it precesses around like a spinning top. And physicists knew roughly what the value should be they had an idea about what the value should be from measurements. And you can do these measurements very, very accurately, but the quantum calculations were extremely difficult. So using the methods that were developed in this theory, several physicists independently worked out corrections to the electron's magnetism. There was this Julian Schwinger and Sinitro Tominaga. And Tominaga apparently worked on this problem for years like every day he'd be doing. He had to have been like obsessive compulsive or something, because he worked. What I understood was he just worked on it by hand.
Can you tell me when was this?
This was in the 40s.
But okay, this is before Feynman started working on it.
No, this is Feynman's theory.
Okay.
So they calculated the electron magnetic moment should differ from the classical value by a very, very small amount, about 1 part in 1,000. And when the experiments were performed, the measurements matched the prediction almost perfectly. And physicists kept refining the theory and the experiment. So this is a nice case of physics, of a physical theory, and then the experiments would do like a mutual dance with each other. Right. So
I guess what we envision as a scientific method, right?
Yeah, and so the Feynman theory, the QED theory, advanced the calculation to a certain number of decimal points, and then because this property it's possible to measure this property very, very accurately. They were able to do an experiment, and then the experiment matched the prediction, and they kept going back and forth, and they were able to exhaust all of the experimental ability to measure it out to, are you ready? 12 decimal places.
Less than 1 part in a billion, extremely high precision measurement of the quantized energies of the cyclotron orbits of the electron gave a precision of better than 1 part in a trillion, 10 to the negative 12. This makes QED the most accurate physical theories constructed.
Sometimes you hear it say quantum electrodynamics is the most accurate theory in the history of science. And so it is very, very.
I guess I know we did talk about this a little while back. Like one of the first things it says is like electromagnetic fine structure constant. Can you relay to the viewers what that is again?
What, the fine structure constant?
Right.
The fine structure constant, this is not what they're talking about, the fine structure constant. The fine structure constant is a measure of how strong the electric field, the electric force is. And it's important because it's a pure number that appears in physics. And physics doesn't, we don't have a physical theory to predict what that number is. We need to measure it. So that appeared by work by a guy named Summerfield, I think, unless I'm forgetting stuff. So the fine structure constant, would sometimes we call it alpha. I mean, we use the word alpha for it. And the inverse of the fine structure constant is approximately 1/137, but it's not exact. It's a little bit different from that. But there's no theory that generates it. It's a pure number.
Oh, okay.
So this is not really related to QED.
Okay. Then that Wikipedia, I don't know why it just started talking about that.
Oh. So there's other anecdote. Well, you mentioned an anecdote about him, about
right. Okay. I mean, yeah. So let me go back to the maybe more relevant questions. So, I guess let's take a step back. At that time when Richard Feynman was starting to work on this, there were some serious issues, as he noted. Well, not just him, but everyone in the field, I guess. What exactly was his insight that brought it to the forefront? And in other words, what is the foundation of QED that adds on to the existing quantum mechanics of that time?
Well, right after I guess one way to put that was right after the Second World War, Feynman kind of fell into a kind of a funk because atomic bomb, and he didn't think the world would last very much longer. He said that he'd be driving around the city, and he'd pass a shopping center or something like that, and he'd go, "What's the point of all of this? Everyone's already dead." Because of the atomic bomb, and he said he lost the joy of doing physics, and so he was at Cornell. And a student tossed a plate up in the air, and it wobbled around as it spun.
This is such a fun story. All right, sorry for interrupting.
What?
like this was what's one of the most inspirational physics stories, I feel. All right, continue.
Oh, so it was rotating around its center, and so like the school logo or coat of emblem was on the side of the plate, and it was like wobbling around. And so he started calculating relationships between wobble and spin. And it turned out that the wobble frequency was about twice the rotation frequency. And for him, it was a trivial problem. And it was just a calculation, but it was an observation that got him thinking again. And he later said the idea of electrons and photons exploring many possible paths came to him soon afterward. And the cafeteria plate, this thing that he saw, it didn't have anything to do with quantum electrodynamics directly, but it restored his habit of playing with problems, and eventually it led to diagrams. So his real contribution, his real contribution led to the diagrams and the methods that became modern QED.
Right.
So
I mean, he invented Feynman diagrams while he was developing QED, right?
That's right. And I really think that that's his major contribution, was that like that guy Tominaga was doing some calculations, and he was
sorry, continue, and then I'm going to ask you a question.
He did these calculations very laboriously and exhaustively, and so Feynman's contribution was to greatly simplify that.
I remember, like, when I was taking quantum mechanics in school, like, we talked about how you can draw these very simple looking diagrams, which essentially is the representation of a large number of otherwise very laborious calculations. But it's been a while. I guess, like, explain a little bit, like, what is happening here as an example, if you can.
Well, his insight was that the particles will communicate with each other through another particle, and so he used this kind of hieroglyphic way of expressing that. And so time is in this case. Well, actually, it doesn't. You can turn them sideways and do relativity that way. But in this case, time is along the x-axis. Okay. I usually see them with time along the z-axis. But he has this, and so what he's showing is an electron entering. It looks like coordinate is down from above, and so there's an electron that comes in, and then it emits a gamma. It emits a photon.
Well, electron to positron, I guess, encounter each other, and then they, like, I guess it's matter and antimatter.
I don't think that's the right interpretation of that. So that's what I'm kind of wondering about.
I'm reading the label.
So I, well, in that case, I don't really know what this is. So, but you can see.
It seems like, I like if the label is correct, it's saying, it's been a while since I've looked at this. Electron, positron, annihilate, produces this gamma, which is like a photon representation. And then this, I guess, becomes a quark and anti-quark pair. And then this anti-quark here radiates a gluon. So it is like hieroglyphics. Okay. Like you have to understand what each of these symbols mean, what these arrows mean, in order to be able to interpret it, and then to draw them out. There's certain rules you have to follow, because ultimately these are representing mathematical equations.
Actually, you can interpret the electron, the electron with the positive charge as an electron traveling backward in time. And so that's a positron, and so they come together and generate, they annihilate and produce a gamma ray, high energy particle, which has so much energy that it can further decompose spontaneously into quarks, other particles. And in this case, this is a quark and an anti-quark, and it looks like you get a gluon.
And I guess the anti-quark is also traveling. It's a quark. Going backwards in time, it seems like. Or is
a quark going backward? That's a little bit controversial. that's not controversial exactly. It's just sort of a shorthand way of thinking about it. Whether particles actually travel backward in time, I think is
how would you know,
something
right?
that
Like
we know.
you can say like a positron is an oppositely charged electron going backwards in time.
That's what people say.
Subatomic particles are quite strange, but that was just showing like, hey, like I'm just saying like this is just like some of the diagrams, some of the techniques, like a very famous technique in physics that Richard Feynman invented while he was developing quantum electrodynamics to help him solve those problems. So going back to the problem of quantum electrodynamics, what major thing was he investigating?
Well, I mean, let's start with like a simple question.
Okay.
I think, you know, so when you look in a mirror, what exactly happens? So that seems obvious, like light from your face hits the mirror and reflects back into your eyes.
Light from the face. Okay.
Right.
Light hits my face, right?
Yeah.
Wait. Light hits my face, then hits the mirror, and then
hits the mirror
in my eyes.
That's right. So we generally learn like about mirrors that the angle of reflection equals the angle of incidence.
Mm-hmm.
So this is all just background here. So if a ray of light comes in, then it goes back out. So that's simple, but there is a problem. The explanation is not exactly true. It's a good like classical approximation of what happens, but it isn't what nature. We don't think that that's what nature is really doing, and so Feynman's insight about this is at the deepest level. The reflection of the light from a mirror is the result of an extraordinary process involving every possible path. People have heard this before. It involved every possible path a photon could take through space to come to get reflected back to your eyes. And so this description comes from, this is the problem that Feynman was working on. And so this is what we call quantum electrodynamics, and we like to abbreviate as QED.
That's like you're using a particular example here, but it's the all path integral approach, I guess. So what is, I guess, I don't know if this is explainable, but I'll ask you, what is wrong with the classical theory of just light bouncing off the mirror and hitting my eyes?
Well, I mean, it doesn't explain why the angle, the more basic question is, why is the angle of incidence equal to the angle of reflection? So when the ray of light comes in and hits the mirror, then it bounces off at an angle that's at the same angle that comes out. So that's an essential physical problem. That's something that classical physics can explain phenomenologically, but we don't have any physics. The physics doesn't. It's an axiom that you establish in first year physics when you start talking about optics. But the real question about why does it do that is very strange and comes from this theory that was developed in the 40s and 50s by several physicists, including most famously by Richard Feynman. So QED, which quantum electrodynamics, is the theory that describes how light interacts with matter, how photons interact with charged particles, like electrons, and it has that remarkable claim to fame that it actually explains why the angle of incidence is equal to the angle of reflection.
That is really interesting. I mean, I'm just reading here. The concept of a photon exploring all possible paths provides a better picture and more explanatory power. Most possible paths are canceled. Most possible paths are canceled out, and only those that lie close to the expected path stated by the law of reflection contribute to the final detection probability. Interesting.
Exactly. Yeah, you said that really. You started reading that really fast. So, like a lot of millennials, and even more. It's accelerated even more with the Gen X and then Gen Z, that. Like Gen Z is, to me, almost incomprehensible a lot of times. It just sounds like...
oh my gosh. All right. Well,
you know.
sorry, I didn't mean to read that fast. I was
Yeah.
just
Well, anyway, so you know,
back to the topic here. This is
so
really interesting. I mean, like, so really, I mean, this shows that like the everyday phenomenon that we just take for granted. Like, really, there's deep physics, quantum electrodynamics, like explaining all of it.
Well, yeah. So, like that's like for centuries, physicists, in particular, natural philosophers, have argued about the nature of light. You know, so is it a wave or a particle? And in the 17th century, Isaac Newton was pretty sure that light consisted of little particles. I think he even wrote the word corpuscle. He said they are corpuscles. I might be wrong about that. No, and so other scientists like Huygens and others, they thought that that it was a wave. So there are some experiments with interference and diffraction, and which really strongly support the wave idea. And well, by when the 19th century had rolled along, people were playing with electricity and magnetism, batteries and stuff like that. And James Clerk Maxwell, who's really a very underappreciated physicist, he should be right up there with Newton and Einstein.
I mean, I think he's highly appreciated in the physics realm.
But the average people, I think maybe our average audience.
Let me ask the audience: who has heard of? Was it James Maxwell? I forgot his middle name.
James Clerk Maxwell. I think he was Scottish.
Clerk. How do you spell clerk?
Clerk.
Okay. Oops. Yes, he is Scottish. Yeah. Who has heard of James Clerk Maxwell? Who has heard of him? If you have, put it down. I mean, okay. Look, we both study physics, so that we're not good representations. But for the audience, whomever is watching, just curious, who has heard of him? All right. Back to Maxwell, who developed a lot of the fundamental theories of
what did he do?
Electrodynamics, right? So classical electrodynamics.
Yeah. What about him?
Well, I don't know.
You have some questions? Oh, well, he showed that light. Well, he basically in a paper that he wrote in 1872 and work that he was doing all during the 1860s in Scotland. He showed that light is an electromagnetic wave. And it's self-propagating. So it's like if you have an electric and a magnetic field and they cross each other, then they will collapse and reinforce and interfere with each other. And so he showed that it was a self-propagating oscillation of electric and magnetic fields. And so for a time, that seemed like the final answer. But in the early 20th century, there were some that picture. Which
I'm gonna put up the famous EM picture, right? That everybody in physics undergrad have taken.
Yeah, everybody. When you took undergrad, when you took physics in third grade,
or anybody taking physics,
or whenever you got that. So you see there's electric and magnetic field, and they oscillate. And time is traveling along the x-axis.
So basically showing how the electric field was represented by E and the magnetic field represented by B is oscillating and actually reinforcing each other. And the direction of the wave is going in the direction of the z-axis here, or V.
It's going in the z-axis. And you could also use Z. You could also use T, time. You could have the time axis, and it would be the same figure. It's just in different units.
Right.
So actually, interestingly enough, I feel a little anecdote coming on.
All right, tell us your anecdote.
So physicists will in the equations in textbooks and whatever, physicists will describe the wave as in this way with the z-axis. So we'll have an equation that will have something times z.
Yeah, look at that.
Electrical engineers, that's right. Electrical engineers suffer under the same physics, right? But they express the equation for waves differently because electrical engineers measure waves at a point in time, at a point in space, and so they will express it. They will kind of their wave is sort of, they have the same wave, but it propagates forward in time instead of forward in space, and see, and so if you're an electrical engineer, electrical engineers and physicists really have difficulty talking to each other about this question.
So,
electrical engineers have the same equations, okay, but the solution, the solution for the engineers is propagating in the opposite direction in a certain respect. I mean, anyway, that's the ending of the little anecdote.
Representation. So yeah.
So
okay. So going back to earlier, so Maxwell in the 19th century developed this electromagnetic wave theory to explain light, which was completely contrary to the corpuscular particle theory that Newton thought of.
That's right. But there were certain experiments in the late 19th, early 20th century. I guess we talked about Einstein one time, and so Einstein comes up a lot. I would hope so. So certain experiments, especially something called photoelectric effect, showed that the light behaves like individual packets of energy. And you also get this in undergraduate physics. Okay, see these packets.
Physics, as Leonard was saying.
What?
You learned the stuff in third grade, right? Elementary school. You said that earlier.
Well, yeah.
Okay, go on.
Okay.
All right. So photoelectric effect. Einstein said, for a while when Newton first developed his theories of light, which by the way, I guess people have been investigating optics for a while, but the point was Newton came up with some theories which essentially portray light as particles. And then came Maxwell, which explained that light can be seen as electromagnetic waves. Waves, basically, kind of like sound waves. They're not the same as sound waves, but point is that they're not particles, they're waves. But then we had a problem with that. And then came Einstein, who with the photoelectric effect, which Leonard, you can explain. I'll just put a picture up.
Well, yeah, he was trying to show there was a certain kind of experiment that you can find in the undergraduate textbook about the photoelectric effect, but it's a very strange thing that if you shine light on certain kinds of metals in a vacuum, and then you apply a voltage to them, then you can turn the power of the light down, and so the light will cause an electron to be emitted. And if you know about vacuum tubes and such, that's a thing. But if you shine light on the metal, and then it will emit an electron. And if you turn the light down so that the power, the intensity of the light decreases, it doesn't matter. It doesn't really matter. You can show that the light is behaving like individual packets of energy, and there's a minimum energy that causes the electrons to be emitted from the surface, and so these packets are called photons. So it's pretty dispositive that the photoelectric effect shows that the light behaves like little individual packets of energy that are called photons.
Right.
And that's also where the word quantum comes from. So a photon is a single quantum of light.
So it's like if you basically like is not coming off as wave. It's like little individual particles, and you have to have sufficient energy in order to essentially induce this kind of effect.
That's right, and that's the evidence. That's the evidence that light behaves like particles. But Maxwell's equations are showing that the energy and the field is flowing continuously like a water wave.
Right.
But wherever you observe it arriving, like on photographic film, photographic film. I mean, if you expose photographic film to very, very dim light, then ultimately you'll just see a single place on the photographic film get developed, and it doesn't matter, and so that's a profound mystery, so you see that wherever you observe the light arriving or interacting with matter, it behaves like a particle. But when it's continuously flowing, it behaves like a water wave. Right. So the answer to this, yeah. So what is it, wave or particle? And
I mean, it seems like it could, that's a great mystery, right? How to resolve that?
So the answer comes from quantum physics, and it's that both descriptions are incomplete in a certain sense. Light behaves like something deeper that produces both the wave and the particle-like phenomenon. And that theory, the theory that explains it, is this theory that we're talking about, this QED. And Feynman had a radical approach.
QED resolves the previous particle theory from back in the day with the what do you call it?
Maxwell's theory.
Maxwell's electrodynamic theory.
Yeah.
Okay.
So here it is. Are you ready?
Yeah.
So this is radical. This is really radical. Feynman introduced a completely new way of thinking about quantum processes. Instead of describing the particles as following like one definite path, he proposed this astonishing idea that, okay, if you have 2 points, A and B, and the photon goes from point A to point B, it doesn't follow a single trajectory.
It follows all possible trajectories.
In some mysterious manner that's not complete, I confess is not completely clear to me. It explores every possible path. I know that if you do the math for a straight line or a simple reflection from one point to another, you can formulate the problem in a way that does give you the answer. But this idea about every possible path is I'm unsettled by the idea every possible, because every possible path
is it every possible path, or is it not every?
Well, Feynman doesn't equivocate. He says every possible path, and that includes a path from A to Alpha Centauri and then back to B.
So like a part of the light like that is shining into my eyes right now, let's just say, could possibly, according to QED, it like one of the possible paths is that it goes all the way to Alpha Centauri before it comes back.
That is one of the possible paths, and so he's able to exclude it. Because all the possible paths are straight paths, like zigging around paths that loop around the universe, and all of them. And this is called the path integral formulation of quantum mechanics. And we've talked about in years past, we have done shows on the minimization principle, least action principle. Okay.
Yeah.
So this is what we're talking about. So the idea is path integral formulation of quantum mechanics. But that idea, it's not really. We also need rules for how these many paths combine to produce observable outcomes. Okay, and so this is what physicists spend years developing the mathematical rigor or the mathematical language to be able to express this using complex numbers. So the complex numbers automatically, when you add them together, and then you take the real part of it. Okay, so the complex number has a real and imaginary part. And so it has the property that when you add them together, then that interference, that extinction and reinforcement automatically falls out. But Feynman didn't want to do that in this book. Because it's math, right? It's so mathy, and he wanted to make this accessible, right? And I think that
I like this stuff, I guess.
I did, certain ideas in quantum mechanics really didn't crystallize for me until I read until I read QED and other things that particularly Feynman wrote about. And so what he's saying is that along the path integral, you have to add up all of the contributions from every path, And so you need these rules for how the paths to produce observable outcomes. And so Feynman and really what I'm talking about is like, I'm really reviewing the entire book,
I mean, Richard Feynman won a Nobel Prize on this and developed this theory. So his book.
He introduced, to me, it's just an incredibly beautiful, simple picture that every possible path contributes a tiny rotating arrow. And so if you go through the book, you'll see these arrows that he has. So the arrows represent what physicists call probability amplitudes. Okay. And I really wish, don't be intimidated by it. Just get this book and read it and see what you can make of it. I mean,
yeah.
There's no math, right? I mean,
other than the book has no math.
The book has no math. Let me see. Let me check.
Wait, you serious?
Let me see. It has some pictures.
Okay, I don't have the book.
No math. I'm looking through here. I don't remember. The book has no math. Okay,
I can't believe that. Quantum Electrodynamics, written by Richard Feynman, has no math.
It has no math. It has no math in here.
That's incredible.
Yeah.
Wait. Here. This is the 1971 book, right? It's just called Quantum Electrodynamics, I think.
Well, mine is 1985, but yeah,
you could have, I guess, updated versions.
Mine is, this is a paperback. Maybe the paperback is different, but is it really that important? Aren't we kind of?
No, I mean, I was just curious on which one.
Anyway, so we got all of these different paths, right?
Mm-hmm.
Okay, you with me? And so the length and direction. So each one has a little path. I mean, it has a little arrow associated with it, and they add together vectorally. So the length and direction of each of the arrows encodes the contribution of that path to the overall probability. And the arrows rotate depending on how long the photon takes to travel the path. So the little arrow is rotating around as it goes along the path, right? And then wherever it ends up, so any arbitrary path, the path that goes up to Alpha Centauri and back, it's rotating as it's going along, and then it comes back in some arbitrary direction, right? And so you add up the contributions in a vector sense.
Yeah.
Right? So you add all the arrows together, and then you add all the arrows together, and after summing all those contributions from every possible path, the resulting arrow tells us the probability that the photon actually arrives at the destination, and that's it.
I mean,
that's the simple.
Which is what we were originally saying about your example of using the light from the mirror reflection, and why angle reflection equals angle of incidence. Because
I remember talking about this briefly in one of our other shows, and I knew I was murdering it. I knew I wasn't doing a very good job of explaining it. But this is the book that will explain this to you, and so I hope that it would give people an idea about it. It's an extraordinary idea, because instead of a single path, the photon somehow explores all of the enormous space of possible histories, and the reality emerges.
Is that so? I mean, just thinking about it, I don't know if this is philosophy, but I'm like, how does it do that? This thing just explores every single possible reality it could be. Somehow how
does it do that? I think in some respect, I remember Feynman saying that somehow it smells all of the different possibilities. And I'll recall something about Feynman.
Oh my gosh.
Okay. There's something about Feynman. I think he told a story about going to South America for a conference or something, and he was either out in the forest or maybe in his hotel room. There were ants, insects, ants, right? And they were traveling along, in a straight line, right? And so he noticed that they were minimizing the They were minimizing some functional between 2 points. And that I think a lot of us, I mean, I've observed this myself with ants. I don't like ants in my house, but sometimes they do come in the house. But you can see that they'll be walking along the wall and they will follow a slightly curved path. And so all of the ants are all kind of smelling the path, and the path. So the ants are laying down a trail and they're following it. And Feynman had this idea, and I guess this is the picture that I also maybe have, is that in some way that we're not really able to understand that this is how physics. There's something like that going on, that each photon is regarding its environment, and in some, I don't want to use the word smell. I mean, I don't literally mean smell, but in some respect,
light doesn't smell things. But go on, yeah.
So instead of a single history, the photon, in some mysterious way, and remember, Feynman said, I don't expect you to, my students don't understand. This is Feynman talking. My students don't understand this. That's because I don't understand this.
I mean,
right? So
it's just like such a hard thing to wrap your head around. I mean, who could actually understand it?
So anyway, the photon explores just an enormous space of possible histories, and the reality emerges from adding them all together. So now we're going to go back to the mirror, right? We were talking about the mirror. Like the reflection, the light that bounces off the mirror, it strikes the mirror and then comes back. So suppose the photon leaves the light source and strikes the mirror before reaching your eye. Okay. Well, the classical physics says something simple happens. The photon hits the mirror and reflects at an angle equal to the angle of incident. But in QED theory, the story, the resolution of that, it's very different. So according to this rule, the photon, the rule we were just talking about, the photon travels every possible path from the source to your eye. And some of the paths bounce off one point on the mirror, others bounce off different points, and some paths involve strange detours, and every path contributes an arrow. I guess the thing is, it's like the channels of possibility, right, all kind of converge on a single one because those little arrows all add together, right? So you imagine adding all the arrows together, and most of them cancel out each other. Why?
I mean, as an example, like say this blue one and the red one are going, the vectors are exactly opposite directions. Or you can figure out.
Yeah. I think that picture you've got there is really, really, really pretty good. Okay, so the idea is, because the arrows point in many different directions, when they point in random directions, they just sum to zero naturally. But there is a special group of paths, right? The paths that are close to the classical reflection point have arrows that point almost in the same direction, and these arrows kind of like, so those arrows that you see along the line there, they add together, and the dominant contribution comes from the paths near the classical reflection angle. So we're not talking about reflection right here. We're just going from one point to another. But so that's the idea. And that's why the light appears to obey the law of reflection. The classical rule that we have, that the angle of incidence is equal to the angle of reflection, it emerges from this quantum process. In other words, the classical physics is what remains after the quantum possibilities interfere and cancel. And I remember getting homework problems, to calculate and all that kind of stuff. So that's the.
Did you already answer these questions? Like I asked, is this a literal picture of reality, or is this just a bookkeeping device to do calculations?
You want my opinion about that?
Your opinion on whether this is actually reality or whether this is just
I do think that it is a reflection of it does reflect what is really happening in the world. I think it is an ontological theory. In other words, it's not just a bookkeeping device. The things about the arrows, is not really that important to the physics. It's that because the complex numbers take care of it. It's just a way of relating the complex numbers, and that's just really part of Feynman's style to try to
Yeah. Oh, sorry. I wanted to, since we're, we could talk about this some more, but I wanted to ask some other questions related to how we actually prove this theory, which you said was done experimentally, up to 12 decimal places.
Well, that has to do with the Feynman diagram contribution to the Feynman diagram formalism for calculating the magnetic moment of an electron. That's just an example. So the measurement is done through by measuring the precession of the electron. And I guess I've kind of forgotten how that's done. That's through has to do with something like magnetic resonance.
This goes back to like what a good scientific theory is, right? Like the capacity, it has the capability to to work for what is commonly observed and explain, what we see every day. But it also has the capacity to be able to be experimentally proven on a very specific thing.
That's right. If you want, I knew you're kind of like poking me in that direction to say something about that. Because we talked about falsifiability and Karl Popper, right? Exactly. And the idea that you're not doing, in order to do science, you need to stay in touch with the experiment. So the experiment, and this is I was reading about particle physics the other day about
of course
Murray Gell-Mann. Murray Gell-Mann. I don't remember whether the standard model. I don't remember whether we did a podcast on that or not.
We've done plenty of episodes in the past on standard model. So for any of our viewers, we can
So anyway, the idea is that if you have a theory about something, then you can make a prediction. And of course, the classical one is that Popper talked about was Einstein, predicting that light would bend when it passed close to the, on a path that from a star, just grazing the limb of the sun, and that it should cause an aberration of the position of the stars, and that was triumphantly demonstrated in 1922 by Eddington, so big headlines, and then Einstein became famous, right? And you got all this tension, and won the Nobel Prize, not for that, but for the photoelectric effect, and then he was big headlines, Einstein, smartest man in the world, and then the women arrived and tried to to take him away, but that's another story.
Hey guys, I know Leonard's talking about Einstein. We're really focused on Feynman here, but the Einstein one, though, there is a past episode where we dive into Einstein's life and contributions, where definitely we talk about the women in his life as well. So
yeah,
go and watch that episode of interest.
And the women that are known, and maybe the women that aren't known. The ones that came and picked him up in limousines and drove him off, and then he came back 2 days later. Okay. So anyway, the partial reflection. So Feynman also explained something even more surprising. Okay, suppose light hits a sheet of glass. Okay, some of the light. Okay, like a glass surface. Shiny, smooth glass surface. So some of the light you've all observed this, some of the light will reflect and some of it passes through.
Well, like this candle, right? Well, this is not really a good example.
Yeah. Well, I mean, in the movie Raiders of the Lost Ark, where are we going with this?
Raiders of the Lost Ark. Let's talk about that.
Indiana. So Indiana Jones knows where the Ark of the Covenant is buried, and the Germans are off somewhere else, doing something else. So they open it, they uncover the thing, and he goes down there, and he falls down in a bunch of snakes, right? So there's snakes down there, and Indy really doesn't like snakes. If you look at that scene very carefully, you'll see that there's a sheet of glass that Steven Spielberg put in front of the actor, and you can see the reflection of the snakes. Some you can see anyway. So anyway, that's the first thing that came to my mind.
Wait. So, okay. You're talking about. Let me see if I can put this up. Okay.
I can. It's just
this one, right?
Yeah. And actually, in the movie, if you look carefully, you'll see a reflection of the snake. I don't know if you can see it in that picture because that picture was probably
in a venomous reptile.
Yeah. So you can see a reflection of the snake in the glass that's in front of him. It's a little defect, not an Easter egg exactly, but well, you know what I mean.
Like this over here, right? That's what you're saying. That's something like that, sort of. I don't know.
I don't know. I don't think I can. I can't see it in that picture, but I mean,
right. Okay, but going back to your point, where's this going?
So when the light hits the sheet of glass, some of the light reflects and some of it passes through, right? And so classical optics treats reflection and transmission as separate phenomenon. So in classical optics, we don't understand that. That's just something we observe, and you can tear your hair out trying to figure that out classically. But in quantum, and the QED shows they arise from the same process. So when a photon encounters transparent material, it interacts with the electrons inside the atoms, and the electrons will absorb the photon momentarily and then re-emit it, right? And some of these events contribute probability arrows, right? Mm-hmm. So not only reflection, but also these probability arrows that we were talking about. And so the arrows from many atoms combine, and most of their contribution reinforce the forward direction, allowing the photon to pass through, but some small subset reinforce the backward direction, producing reflection. So there is a kind of like not the absolute longest probability, but like a little mountain of a little hill of probability for the photon bouncing off the surface like a rubber ball. So that's a fantastic result from QED instead of the result of quantum interference among many tiny contributions. Okay.
That's I mean that's rather interesting that it's able to combine, like it's more. Yeah, like classically, you're going to have to split it up into two different phenomena, whereas this, you have one theory which you can explain.
Yeah. So there's three simple rules. Okay. So Feynman in the book in QED, he summarizes there's just these three rules. Rule 1: a photon can travel between 2 points along any path whatsoever, past the moon and back. Okay. Rule 2: when the photon interacts with an electron, a small probability amplitude is produced. The particle involved here is the electron. Electrons, and mostly it's electrons that have to do with ordinary, light emission that we see, and because those are the most mobile charge carriers that we have. There are other protons are charge carriers also. But electrons emit and absorb photons, and that's how electromagnetic forces operate. Rule 3. So there's two rules. Rule 3: to find the probability of an event, we add up the probability amplitudes. That's the little length of the little arrows that are rotating around when they arrive at a particular point. We add up all those probabilities, and then we square the result. That's just a thing. Okay.
Yeah, I mean that's like okay, yeah.
And people who have taken quantum mechanics and are listening to me talk about this, they know all of these rules. They know this formalism,
right?
But just with a very erudite, smart way of expressing it, and with Greek symbols and stuff like that. Okay, so those rules, those three rules, they capture the essence of quantum electrodynamics, and from them we can calculate everything from atomic spectra to scattering experiments. So now I'll pause.
You will pause? Okay, let me see.
Pause for a moment.
Yeah, I was looking at this. This book doesn't have Feynman diagrams, weirdly enough.
Feynman diagrams.
It does not have it. It just writes everything mathematically. All right. Well, this is a pretty basic textbook, so maybe.
Anyway, get QED and read it. I mean, maybe he'll lose you. I think some of my friends.
So go on.
They usually there's been a few people that I've offered that book to, and they stopped being my friend.
You've offered the Feynman's quantum electrodynamics book, and then after they tried reading it, they're not your friend anymore.
They changed their phone number and never spoke to me again.
Oh my gosh.
But but I mean, I honestly, but not everybody. Some people say, yeah, this is a really good book. But
I want to read it now that I probably should have read it.
So he does introduce Feynman diagrams, these strange diagrams. I think he bought a van in the early 70s, and he decorated it like it was like one of those vans that's in Scooby-Doo, that van. So I think it's the same make and model of the Scooby-Doo van, but I could be wrong about that. Maybe, and then he decorated it with Feynman diagrams, and then they drove all over California.
So he was just doing this because he's Richard Feynman and he has a great sense of humor.
He had a sense of humor, yeah. Feynman diagrams. So physicists often represent the interactions visually using those diagrams, and these are called Feynman diagrams. And in these diagrams, first of all, straight lines represent electrons, wavy lines represent photons, and then since then, other kinds of lines like spirally lines and dotted lines and stuff like that represent other kinds of particles. But for the basic idea, where the lines meet, a photon is emitted or absorbed. So if two electrons, so each diagram corresponds to a particular quantum process, and more complicated diagrams represent more and more complicated interactions.
I want to go back to no need to dive into the extreme science of 12 decimal places. Can ask that another time.
Well, that is important though, because that is phenomenal. Okay, I can't understate that. I mean, 12 decimal places. You get a number out of a calculation about physics, and then you measure. Much of it has to do with the ability to measure the magnetic moment of an electron, which, because it's processing around, you're able. And
electron, quantum electrodynamics predicts it, and actual theory matches, not actual theory, actual experimentation matches it to 12 decimal places, which is remarkable.
And much of the remarkableness about it has to do with the ability to measure it out to that far.
Yeah.
Okay, that many decimal places.
Right? Does this mean that this is the final theory of electromagnetism? I have to ask.
Well, no, because we talked about gravity.
Yeah.
And
okay.
Okay. We have to produce that. We have to merge that theory. Also, this doesn't really yes. I mean, much of this has to do with generating a standard model.
Well, what I'm saying here is that, obviously we don't have a complete theory of quantum mechanics since we don't. It doesn't include gravity. But in terms of electrodynamics or electromagnetism, whatever. Is this a final theory that can cover that?
Is there a final theory that can cover?
Well,
that's the question again. I drifted off there.
Well, what I'm saying is understandably, this is not the final theory of quantum mechanics because this is only covering primarily electromagnetism.
In QED, it's only talking about electrodynamics,
right?
But there's particle physics, which has to do with gluons and the weak force and neutrinos and gluons and quarks and stuff like that. Right.
Okay.
So people do have a kind of hadronic string theory involving hadrons, which are hadrons are protons and neutrons.
Okay.
They seem to be two species of the same kind of thing. And that got into where Gell-Mann and the early,
So I mean, I think I answered my own question actually looking at it, in the sense that like, so Richard Feynman also did a bunch of Feynman lectures, I guess, different overall over various aspects of physics, and he discusses the meaning of quantum electrodynamics, the problems, then describes the rest of physics, giving a look at quantum chromodynamics, the weak interaction and gravity, and how they relate to quantum electrodynamics.
So quantum chromodynamics is the extension of this theory into particle physics, and then we don't know how to do gravity.
Right.
All right. The string theory people sort of became unmoored from experiment, and then they
unmoored.
Like I said, unmoored. Yeah. Okay. Unmoored. Like when a ship comes up to a dock and it's tied up. Okay. I think we can say that's been, so you undock it and then it kind of drifts off. So string theory has drifted away from experiments. So the experiments, we've exhausted the ability of the experiments to measure anything, but the string theory is such a robust or expressive mathematical structure that actually it can show anything. And so, and therefore you can publish hundreds and hundreds of thousands of papers that can be written about string theory without having to worry about the experiments.
I guess I mean I don't want to get into this string bashing sort of episode here.
No,
string theory bashing episode, but
that's I live for that.
We've done plenty of like bashing of string theory in past episodes.
Well, but it is a problem though. It's quite shocking that these thousands and thousands of papers are being written, and people don't know that you need to stay close to the experiments, right? So,
right.
And,
quantum electrodynamics is a wonderful example of a good theory in that we are able to experimentally prove it to that degree of precision.
Right.
Whereas string theory is, according to Leonard here, and maybe I agree as well, is not a great theory in that you don't really have experimental proof like it could.
Yeah.
So
and there are physicists out there that are noting that, like Turek, Neil Turek, that we discussed one time. And
we did an episode on Neil Turek a little while back.
So, but anyway, so actually there was a Feynman diagram. So we know about the Feynman diagrams. There's this problem of infinity that he has a little chapter, or he discusses to a certain early attempts to calculate quantum interactions in the, not without using the Feynman diagrams. They led into serious problems having to do with the equations often produced infinity as an answer. So like an infinite energy, infinite mass. And so these obviously can't be true. They can't be right. So physicists develop a method called renormalization to deal with this issue. So the renormalization, the idea is subtle. Certain quantities in the equations are not directly measurable. And by redefining these quantities in terms of measured values, the infinities cancel, and the result is a theory that produces finite predictions. So he talks about this in there. And so the method was refined by three physicists, a guy named Schwinger, Julian Schwinger, and then the Tominaga that we talked about, and also Feynman. And that's really, with the Feynman diagrams and this renormalization, that's why they shared the Nobel Prize in 1965 for that work. And so as I mentioned, the unbelievable accuracy, striking success of QED involves that magnetic properties of the electrons. So the theories experiment agreed to more than 12 decimal places. I think it's true that no other scientific theory has achieved that kind of a level of precision. So it really is something that you should, like swoon over. You know, like
Hey,
okay.
did you
It's one of the
want to do that again?
no, I don't want to do that again. It's one of the strongest confirmations of modern physics. There's only
Okay,
you only have one chance. You can reset the dial the thing, the little slider on the YouTube video on the video.
I mean, basically, according to Leonard, you should swoon over the implications of quantum electrodynamics.
I think so. So, but despite its success, QED raises it. What it raises philosophical questions. Okay.
Well, I mean, I was hinting at that throughout this. Like, I think I asked you earlier whether like you actually believe this.
Yeah,
and you said you do. That somehow reality fundamentally is just probabilities. Like everything's happening in one.
Yeah. Well, if the photons explore every possible path, what does it mean? Yeah, exactly. That's a good question about what does it mean about reality. So do all the possible paths exist simultaneously? I think that it's something like that. Or is the theory simply a calculation tool? So even Feynman resisted trying to answer those questions. He just wanted to, he was perhaps less philosophical. And I do think philosophy is important. Philosophy of science is important. I was watching a YouTuber, a famous, an important YouTuber, talking about belief. You know, like some scientists say, "I don't believe things." I go, "What? What do you mean you don't believe things?" It's like because they don't want to be drawn into the classification of people who just accept things on faith without evidence, you know, but just the fact that you rely on evidence and that it's veridical requires faith. And we can argue about that. We should do another podcast about that. But not today.
What do you want to argue about? Not argue, discuss.
Well, the idea that some scientists don't want to use the word "I believe" or "I have faith." They don't want to say those words, but that actually, you know, Karl Popper, you know, would say that there is this thing called induction, and that if you have a measurement, if you observe something and you set up the conditions again and you observe it again and you get the same result, the fact that you're getting the same result and then you rely on that as a veridical inference about reality requires faith. It's not philosophically defensible to say that. So, but we can talk about that another day, maybe.
We can. I mean,
and I think Feynman. I don't think Feynman was interested in that. I think he would just kind of like wave that off. I think he might be. Sometimes you hear people say, like when I was learning quantum mechanics and I was wondering about this very thing. There was this idea. So, well, these are questions that you cannot ask. So,
that's a really good point, because I recall when I was taking his classes, I mean, it was like you just do the calculations, right? And
so
just do the math.
Yeah, but then so you do the math, and so it gives you answers. And so if you're an engineer, and not to be knocking engineers, okay, don't point at me and say I'm knocking engineers, because they do important things and they do things, they know how to do things that physicists can't do, like build an electric motor.
So, you know? not going to knock engineers at all. Go on.
Yeah. But the idea is, like, I don't really care about the philosophy. I care about the answer, right? But you know, if you're a physicist and you're trying to explore and understand how the world works, those kind of questions, like what's really happening? Is the photon going through two slits at once? It does become important, and it has emerged in recent years because we realize about the violation of Bell's theorem with spooky action at a distance, that kind of thing, and also the merging of quantum effects and classical mechanics with black holes and the Big Bang. We can't. I don't think we can make any more theoretical progress without understanding how those things go together, especially black holes and the Big Bang. But that's for another day. So the classical world experience is not the fundamental layer of reality and emerges from deep quantum rules. Those rules that Feynman was talking about are everyday intuition formed by large objects, and slow speed simply does not apply at that microscopic level. So Feynman,
right. So
I was going to say,
is ultimately does the universe not operate according to human intuition?
I
don't even know what human intuition is. I mean,
I'm afraid to say, there is the holographic principle.
Oh my gosh.
Where the idea that at that point where the universe appears to be expanding around every point that we know of, it's all expanding. At a certain place, 14 billion light years away, the expansion reaches, or at some point, the expansion rate is faster than the speed of light. And so everything outside of that horizon is utterly unobservable, utterly elsewhere,
right?
And not accessible to us. But on that surface, there is a kind of holographic. There's an idea that all of the objects on that surface, that's billions and billions of light years away, and receding from you, that surface has all of is a volume that encloses the universe, and that everything going on that surface reflects a entangled element of reality. So, when I hold up my coffee cup here, all of the atoms here have an entangled partner on that surface far away. So in a sense, everything inside the volume of the universe
is contained on that.
Is contained on that surface.
That's crazy. Okay, did we ever do a show on holographic principle? Maybe we did.
Well, we talked about Leonard Susskind.
Yeah.
And that was a good show. So go back and watch that one again.
Yeah.
But we can talk about it again. So the idea is, like, if the photons are exploring every possible path, what does that mean about reality? So the question is, do all the probabilities exist simultaneously? Or, so I think Feynman would think that it's just a calculation tool. I think he would resist trying to answer those questions, because he would be the guy that would say, shut up and calculate, right? Yeah. But you probably could get him interested in it. Leonard, by the way, since we brought up Leonard Susskind, Leonard Susskind did try to, when he was a graduate student, he tried to, or early career professor, he tried to talk to Feynman, like in the men's room before a lecture.
And then what happened?
Literally, he was trying to talk to him about quantum and black holes. And so he did get Feynman interested in it briefly, but I think ultimately Feynman said, he just threw up his hands and said, look, black holes are about big classical big things, and quantum mechanics is about tiny little things, and we're never going to be able to merge them. So I think
kind of gave up and be like, okay.
I think Feynman was vaguely interested in that. Okay. In that area, but he was interested in so many other things that he didn't follow.
I just realized we did an episode on Richard Feynman like 2 years ago. Did you know that?
No, I'm starting to suffer from like that cognitive decline that they.
Oh my gosh!
No, actually, I do remember it very well, and I think it was a pretty good show. So
this is hilarious. But yeah, I mean, like, when we did episode 128 2 years ago, like that was when but we didn't go in depth and talk about quantum electrodynamics. It was just about Richard.
So it was also so Feynman was not interested in quantum mechanics, merging quantum mechanics with black hole physics, but that was the area where Stephen Hawking, went off on a journey. So, but the idea, but when we're talking about this book, Quantum Electrodynamics, it is the case, that Feynman does say, our everyday intuition that's formed by large objects and the slow speed, it just doesn't apply, and that's consistent. So anyway, we're running on. How long have we been talking?
I don't know. Like, the point is, I guess overall, it's up. This is sort of like philosophical, right? There's not really a definite answer here, like whether the universe is operating according to your intuition or not. But
that's true. So, I mean,
like you said, like you talk to different physicists, and they're going to tell you different things, and even the people who has developed these theories. So
yeah, I think it is true that in lectures and so forth, Feynman would tell the audience, I'm not going to tell you how this works because nobody knows how it works. He would say it's something like that, So he meant our everyday intuition simply doesn't apply. So, but quantum mechanics, quantum physics works perfectly as far as we can tell. So, but the results resist ordinary explanation. So anyway, I just had some so the final thought I have about this is so if you look in the mirror, remember what's actually happening. The photon leaves your face, explores every possible path through the universe, or at least you could model it that way. And each path contributes a tiny little rotating arrow, and all the arrows add together, and out of that vast quantum calculation emerges the simple reflection you see. So nature performs this calculation instantly, trillions of times every second. And the quantum electrodynamics is our attempt to understand how. And it works. And better than any theory in the history of science. I don't think that's an exaggeration. And so, but that as we've been discussing, that message remains unsettling. So
indeed,
anyway, it is stranger than we can imagine.
The theory that is shown to that precision level of and also have such implications is very startling. So
yeah, the end. That's all I wanted to say, or
right.
That's all you would allow me to say.
Yeah, that's funny. My friend Joe has a funny comment. I'm just going to put it up. You about swooning earlier.
I have swooned, fallen into a black hole, not reflecting or reacting anymore. Cognitive decline indeed.
All right, that is good. All
Joe,
right.
What's Joe? Can I ask what is Joe a boomer or who's?
I don't want to put people in categories like that, but sure.
Never mind. I'm a proud boomer.
I think he's probably about, I don't know how old you are, Leonard, but I'm not going to say on the show.
430 years old.
Yeah, there you go. Well, you are an alien sometimes.
That's true. I talked to the mothership.
Yeah. Okay, so I think we're gonna wrap it up. So you already said your last words. For everyone out there, what's that?
My last words for today.
Okay.
I will have other words later.
I was gonna comment that I thought I did not know how to put the banners back on, but we are. I guess, I guess I could. All right, thanks to Chip Burge for actually making the theme song. Otherwise, like I was gonna say, support the show. You can go to patreon.com/sgt2onspace. Thank you for those who are supporting either, just supporting for free or just a small donation. Thank you for all y'all. And obviously, we've had a hiatus for quite some time. Let's see if we can get this back on track on a
well, it's spring. Okay, we're about
spring. So
the dark days of winter are behind us.
So we took a little break. But anyways, we keep posted here. I mean, obviously SG2 on Space. There'll be another episode most likely in about a week. Or two, and on another exciting space topic or science topic or something really weird, because that's how we like to.
You're responsible for the weird things.
I am. Well, that's true. So for the weird things, for people who have not watched this show before, in the past,
if you look at the playlist, we have talked about UFOs. We've talked about the Mary Celeste. What happened to the disappearance of DB Cooper? Bigfoot.
Bigfoot.
Where Leonard literally drew a very nice picture. That one's a really good one. So. But yeah, feel free to watch those for some other episodes, and feel free to leave feedback, of course. All right, we'll be back. So with all that said, take care, everybody, and have a wonderful day, wherever you may be in this universe.
All right.
So.
Namaste, shalom, and mwah.